So this is the first of many things or presentations that I want to do to try to give you guys a chance to avoid the mistakes that I've made. So what I noticed when we have been building out all these systems for clients is that we tend to repeat ourselves. And I wanted to make sure that we document the kind of things that are common mistake that we do. And this first is the first out of at least 10 white papers that I'm planning to write. So this is also backed up by a white paper that has more detail than this presentation. In this one, I want to take the top thing that I've seen actually, and that is that's software solutions are put out into the edge without concerns for some of the network challenges that you will find out there. And I'll share some of the experiences that we had, some of the use cases, and some of the things that happened. It's a fairly technical, I can make it as technical as you want, but I'm trying to, for someone that is not that familiar with networking challenges, to at least give you a chance to understand what you need to think about, what you should look at. Okay, so without further ado, let's move into what we're going to look at. So there are a set of challenges that a software engineer typically do not experience. And the reason for that is most software engineers that are starting to work on the edge have been used to working in data centers and the very controlled servers, so that if a network goes down, they were never to blame, right? They could say, hey, oh, the reason why my software is not running is because the network went down. Well, you can't do that on the edge because network will go down. You're going to have intermittent connectivity. You're going to have bandwidth restrictions, and you can't just blame, the lack of network or lack of speed in the network. You have to actually have program for that. You need to look at latency variability, so-called jitter, network security, obviously. Now, some of these things I'm going to come back to in subsequent seminars in more details, but they're all related to networking. And one of the things that is a little unfortunate when you start working in distributed computing in general, but certainly in edge computing, is that most of these software ideas we have are based on mathematics and not on physics. So that we assume that the computer will work instead of assuming that things can go wrong. We assume that messages that are sent out are delivered in real time. They're not. It takes some time. We assume that the messages are produced in some order and will be received in that order. That's not true. And this dates back to old computer science. There used to be Dijkstra and another guy called Carl Hewitt that were kind of competing about how we should think about software. And Dijkstra clearly won. So in most universities around the world, we're teaching Dijkstra, or the Dijkstra's way of looking at a computer. But I think what you'll experience as you go to a more and more of a distributed network is that you have to think like Hewitt did. And Hewitt is the guy behind the so-called actor model. And I'm not going to teach the actor model here, but I just want you to take into account that some of the techniques that you used as a software engineer when you were working in a very controlled environment where someone else took care of everything around the infrastructure, and you could assume that the infrastructure was working, cannot be used at edge computing when you go to edge computing. So there are different challenges. Well, let's start going through those, and then I'm going to go through some use cases. So let's start with the intermittent connectivity. So this is the idea that you're not always online. You imagine, for example, that you had a central database and the edge computer is supposed to connect to that. Well, you can't really assume that you always can get that connection. You could have a moving vehicle that went into a tunnel and therefore you cannot access the network. You will get disruptions of data. And for that could be very crucial, or things that you have to deliberately design for. And it's particularly in sort of mission critical applications, like say controlling the energy grid. There might be a huge spike of consumption in a certain factory, for example, that you really want to react to maybe direct more current towards one of the transformers, but you can't do it if you don't get the data. But are there other ways of detecting it? There are other ways that you can discover it, but you have to design for it. So some impact, typically data synchronization, right? You have inconsistency. Some node in the network knows something that the others do not. You may have, services that are not available at all times, and you have to plan for it. Your software can't go down. It can't crash because of that. So there are different strategies, but just imagine, for example, an autonomous vehicle, Tesla probably being the one that is further along these days. If it relied on messages from a central site to be able to navigate, for example, maybe there is a traffic ahead or an accident, the car has to be able to detect it and not rely solely on a central message coming down. You need to be able to typically handle the case, and you have to assume that the network is done. You have to test for it, and you have to have a strategy. And that often includes some local data processing and storage. In the case of Tesla, they would be able to do the navigation and discover these things based on image recognition and a massive deep neural net. But you have to also say, okay, I'm not able to handle it. What is the best thing I could do, right? Can I gracefully shut down something? Whatever you need to do, but you have to plan for it. It has to be part of your plan. So you need to evaluate things like fallback mechanism and redundancy. You might evaluate using predictive network maintenance, things you could do now with AI and ML. It's pretty fantastic. You definitely need to provide a testing environment in which you're able to simulate these failures. It's amazing how many systems I've seen that have been put out in the field where they never actually disconnected the network cable and everything goes down and crashes and burns everywhere just by simple things like that. And even if you test in a local environment, you can easily create things like you can use Netflix Chaos Monkey, for example, to bring services down. You could put in various network proxies to simulate network failures. But it seems like most companies don't. Another challenge that we often see at the edge is just bandwidth constraints. If you're hooked up to let's say a 5G network, you might have really good connection. I mean, you could get upwards of 100 megabits per second there. But if you're on the 2G, you're basically down in the hundreds of kilobytes or less in terms of speed. 4G, most people have never tried their solution on 4G. They have tried their distributed solution. They tried it in a network that they have in the lab, maybe with a router that is 100 megabit or gigabit router. And as soon as they get out in the field and they're connected maybe to a 4G network, everything falls apart. Also, I've seen a lot of mistake done in the AI ML space where they're assuming a certain speed of data coming in. Let's say, for example, you have an operations center and you're assuming that you can send all these video streams into the site. They may have tested it with one video stream, but now all of a sudden they got 100 video streams or 1,000 video streams. So as you add more devices, what happens? And you have to try this out. You have to test it out before you go into the field, because it can be very expensive to fix, or even worse, it might not be possible to fix. So some of the strategies that we've seen being effective is to introduce data compression and optimization on the edge. This is one of the reasons why we're doing edge computing. we've seen reduction of traffic that is very significant by, for example, well, we've seen certainly 99% compression by just looking at the data, taking away the data you don't need, for example, filter things out. Even if you have to send the data up, often the data is sent in XML or JSON or so. By just doing simple compression, you can do massive saving. But the edge processing also allows you to do other things. You could filter out things. So for example, if you have a sensor that is super chatty, that is producing thousands of messages per minute, you may only be interested in sort of a vector of what it produces or the average over the last minute or something simple like that. And you can dramatically reduce the traffic. I'll give you an example. So I had an asset management system that I sold some years ago, or I sold the idea of, and we were using messages to, or we were tracking different things in the field. We had a few 100,000 things we tracked, and they sent messages in to the central server. Well, that was some kind of ASCII message that some developer of these devices had done. So I took over the firmware of that, changed that to use Apache Avro in my case. And the 400 byte message that was there before now became an average of 18 bytes. You know, that's a massive saving by just changing the underlying protocol, but it has to be a concern. You see, when you're working in a data center, you don't typically worry about these things, but when you get to the edge, you have to. Another thing that often can help is prioritization of the data traffic. That does require some edge computing as well, but let's say, for example, I'm monitoring a patient and I get a constant set of information about the patient. The patient is having a heart attack. I don't want that heart attack to sit in a queue waiting to be transferred. I want that to go to the front of the queue and being sent up immediately. So the ability to prioritize data traffic where you're bandwidth constrained is also quite important. And you can also use adaptive algorithms where, depending on the environment or what is happening at the edge, you change the behavior of how you approach the sensor input based on your knowledge of the domain. And of course, you can always upgrade the network, right? If you were on a 4G network and you will go to 5G, you probably see a 10x improvement depending on how much traffic is around you. And so there are other options, but they can be quite expensive. Another thing that it seems like people have misunderstood is this concept of latency. So latency has to do with how long did it take from the event was discovered at the edge until you can react to it. Let's say it shows up on the dashboard, for example. The time that takes is what we call latency. However, what's more worrying in most cases is what's called jitter, which is the variability of the latency. So most people measure sort of the mean latency, but it's equally important to know what is sort of the worst case latency. Worst case will be the message never gets there, of course, but what is an expected, is, let's say we have an average latency of 0.5 second, and is 1 second is that a very special case, or is that something I can imagine happening once per minute, for example? So the two things you should measure at minimum is sort of the average latency and your jitter, and perhaps create some kind of normal distribution curve like the one I see here. And then you have to test based on that. So you have to inject this knowledge back into your test environment so that you get to experience those before you put the data out in the field. For many that are working on the edge, the actual change of the software on the edge could be extremely expensive. Or you can use some kind of orchestration platform like Pratexo have, so you can actually push it out. But it's really important that you take this into account and you bring that into your software and you make sure you test under those conditions. Okay, so this variability in latency or jitter is very important. And I see all kinds of craziness when people are starting out. For example, they don't time their observation, or so the time of the observation is not in the message itself. So they timestamp the data when it comes in. So imagine, for example, you're looking at a heart monitor and you're getting the electrical signal once, or maybe you measure it 100 times a second, but all of a sudden you don't get data for a second because of jitter. Okay, well, all of a sudden your heart monitor will look like a flat line for that period, and you might do really bad reactions to that. I mean, maybe an extreme case. But you also see this in user experience. Maybe you have video feeds that come in and the video feeds stutters. And what I've seen is people that then learn from that stuttered video feed. So they apply machine learning algorithms on that. And those machine learning algorithms now are completely confused because they don't know that it is actually a stutter in the video. But you can also see it in real-time analytics, things that don't move. So there are things that we can do like timestamping when the event is and handle backfilling of event. And it could be a challenge for real-time decision-making too. And the jitter is there in the network, and it's very rare that you can do much about it, particularly if you're using one of the mobile networks. It's rare that you can do something about it, but you can plan for it, and you can make your SLAs based on the jitter on the network itself. There could be synchronization issues. It has impact on load balancing. There's all kinds of issues with this. So some of the strategies that we applied, which I think are worth mentioning at least, is of course edge computing. So in our case, we often put out a computer that has sufficient power to do the actual processing online. No, sorry, without going to a central site. This obviously reduces our dependency on network latency because we never go on the network. So if we are able to do the real-time decisions locally on site, then that takes away our latency dependency. We also use latency-aware application design, meaning we set timeouts. We use asynchronous communication pattern. We do things like graceful degradation. We know how to backfill data. Let's say, for example, you have a stream of events. We don't use the injection time of the event, or we don't use the processing time of the event. We use the actual observed time of the event to do our calculations. You can also, in some cases, do various form of dynamic resource allocation. You can use things like some of the fancy SD-WAN solution, for example. And sometimes you can also improve latency by just spreading things out, right? So if your data center is sitting in Phoenix, Arizona, and you're processing and a site that sits in, I don't know, London, UK, you could probably have moved that whatever data processing to a London data center rather than running it across the Atlantic. Network security, another thing that we see. Those that are, well, I should say this. So one of the things that we do at Pratexo is we often are coming behind an effort of going on the web edge. So our customer may have spent a year or two trying to build out an edge solution, and it's cost them millions of dollars, and they giving up on it, or they come in actually very skeptical to the whole idea of edge computing. So we get to see the mistakes they've done. And some of the mistakes that I mentioned already are obviously mistakes that we've seen our customer do, not only us. But and network security is one of these things where when you go to the edge, you have an increased attack surface. There are certain things that you reduce, but there are new challenges. Right. So, for example, if you put a edge computing on the building site, you may have to physically constrain access to that computer, or you need to perhaps use encrypted disks or so because you're afraid of someone actually physically going and connect. You may have to prevent USB connections. There are all kinds of things that you have to worry about. You also may have to look at the communication from that site to the router, for example. So from your edge computer to the router, can someone put a network sniffer in there? Can someone sniff at the router level? Where can they attack us? Encryption goes a long way, at least until we get quantum computers, right? But it has to be one of these concerns that you have. Data security, privacy concern. Often you don't want privacy data, so you want to at least make sure you adhere to the laws or the rules of the domain you're in. Inconsistent security policies can become an issue because often when you get into edge computing, you are talking to multiple devices. So you may have everything secure, but you are talking to a PLC that is standing out there and is collecting data that in a way that is completely open, right? So you have to look at you often have to try to enforce some consistent security policy across multiple vendors. That can be a challenge. There might be resource constraints as well. Encryption is expensive. If you have a very lightweight computer out there, maybe it's not able to do the encryption, or it's stealing too much CPU resources from your domain, or the encryption is too costly in terms of latency, for example. So you have to look at that as well. And because the network is not as reliable, you have to deal with outage. And it can be really hard to separate an outage from an attack, right? So depending on your domain, again, you have to think about this. Okay, if a machine goes offline, is it because it truly went offline, or is it because someone is attacking us or disconnected it from the network or stole our computer, whatever it is? You need to maybe introduce a secondary means of seeing whether you're being attacked or if it is just a normal outage. So some of the strategies we apply is security by design. Right, so security has to be a concern from the very beginning, and you have to ask the right questions. Introducing robust authentication, access control, regular security updates and patch management, end-to-end encryption where that is appropriate. And it's important that it is where it's appropriate. So for example, we built the system for tracking dogs, sort of in rescue efforts and so on. We could direct the dogs or create these take swarm ideas to direct the dogs to the right places to search. Let's say there's an earthquake and you can let the dog loose to find survivors. No one cares about securing that traffic, right? I don't want to spend extra time or effort or additional resources on encrypting the traffic. What is important in that domain is that the computer is as light as possible. A dog can only carry at max 20% of its own weight before it gets hampered. It probably should get into 10% of its weight. So what was important there is that the computer lightweight, right? Are the sensors that we put on it, it's the camera we put on it, are these lightweight? So it's not encryption every time, right? Well, we're not trying to create like Fort Knox on the edge, but we're trying to create a system that is reasonably well protected. And that might introduce things like intrusion detection and prevention system, because the site might be remote, might be unattended. We might have to do segmentation or micro-segmentation to isolate networks, to contain breaches. And I think it's important also that as a company, you establish regular security audits and compliance check, where your security experts are evaluating the solution you're putting out there, or you hire a third party to do so. Now, this leads to a set of architectural concern. A not so well-known paper out there from IEEE that is called 1471-2000. This, I think, is one of the better or more interesting standards that I've seen, and it was written, I think, back in the 90s. But the idea is when you are attacking a particular problem, when you're trying to build something, there are a set of concerns that you need to address. And for years, I was teaching this class called architectural thinking, because what some of my clients had figured out is that you take a really good engineer and you promote them to an architect, and you lose a good engineer and you gain a terrible architect. Same thing with managers, right? So how can I teach someone to think architecturally? And the key to this, I think, is an architect has to hold many hats. It can't have a single hat. You may have to put on your security hat, right? And say, okay, now let me look at this problem from a security perspective. What are the questions I should ask? What are the things I need to worry about? Maybe you have a scalability hat. So you put the scalability hat in. You put a recruiting hat. Is it easy to recruit people to work on this, right? You have all these hats. And a colleague of mine and I worked together on building out these architectural concerns. And I think we had somewhere in the order of 70 of these concerns with a whole set of questions we would ask. And you can imagine making a choice as being think of it as a spreadsheet. You have all the concerns on one dimension and all the option along on the second dimension. And you need to select a good balance between these. Now, I'm not going to go through all these architectural concerns. Some of those are in the white paper. Actually, that is from the white paper. But let me at least address a couple of these architectural concerns, like distributed data processing, state management, synchronization, testing, perhaps. So the first thing is, let's acknowledge what we're trying to achieve, right? And in big data, they're saying is, don't send your petabyte to the algorithm, send your algorithm to the petabyte. Okay, this is, I think it's, you know, the motto of, you know, Apache Hadoop and Apache Spark and so on. So you are collecting all this data on the edge. So we have a power company in Norway, for example, where we put out a 2 terabyte disk on each edge site. What happens now is we get all this data in from the sensors and we store them locally on the machine. Now, what is important to us to take advantage of this, because these may be connected through a 3G or a 4G. In Norway, it's mostly 4G, but some 5G. We don't want to send all that data up. Each site is producing, you know, gigabytes of data per day. So we don't want to send that up, but we don't want to lose it either, because there might be a machine learning algorithm or some kind of insight that we get later. So what's the key is that we send the algorithm down to the edge machine and say, hey, can you look through your data and figure out what's happening? So that's or figure out this, can you answer me this question? So we send the query to the edge rather than trying to take all this massive data and send it up to the cloud, right? And this is what we're trying to achieve. And in general, it's usually a good idea to always process the data at the first point of what I call a full event horizon. That means you have all the data that you need, right? So for example, if I'm on an edge site, and I'm trying to control let's say a valve, open up some valve. If some tank is getting too or someplace the thermostat goes up too high, I need to turn on this valve. There's no reason for me to send all this data up in the cloud and then make the decision there. That algorithm, that rule can be downloaded to the edge device, and the decision can be made there now with no latency and so on. But it's interesting that you can do this with analytics also. So imagine that we have this 2 terabyte disk and a quad core processor sitting out in all these edge sites. And let's say they have 100,000 of these edge sites. That's a pretty massive processing cluster that we put in place, right? Say quad cores of 400,000 CPUs, right? Let's say we have a 16 gigabyte space, right? We're talking about some massive compute cluster if we're able to send the algorithm to the edge. Now that has a set of other challenges. Ideally, to be able to do that effectively, you should have a studied algebraic topology, or what do you call it in the US? I'm Norwegian, so it's called category theory here, right? So that you can design algorithms that actually work in this distributed space. That's not hard if you're sending data down to make just a conclusion for a site. But if you're trying to, for example, let's say we had medical data spread out in all the hospital and you're trying to see a COVID spread, you're trying to look at how it works across all these sites. So the event horizon for you isn't just the hospital, but it might be all of the hospitals in a region, for example. Okay, let me give you an example of this. So this is an example that I built actually before we started Pratexo, but Pratexo was basically based on 15 years of experience building these different systems for various clients. So this is a remote patient monitoring system that we built. They wanted to scale up to about 1 million patients. This might be strange if you're calling in from a different country, but in the US, we have a fairly significant issue where the insurance company and the hospital or the providers have a conflict. If you have a heart attack, for example, if you go to the hospital and you get some stents or whatever, and they send you home, and you get a new heart attack, let's say next week, then the hospital is on the hook for that cost. However, so the hospital wants to keep you as long as you want, as long as possible, where the insurance company want to send you home because it costs $30,000, $40,000 a day sometimes to keep you in the hospital. So the idea was to have a set of, this customer had was to have the ability to monitor a patient in their home. So they wanted to monitor upwards of about 1 million patients. Each patient would be hooked up, so that's what you see at the bottom here, will be hooked up to a set of devices. It could be something really simple like a scale or a thermometer, but it could be an EKG, or it could be all kinds of other more fancy equipment. There was also an Android tablet sitting at in each home. And this is for the nurse or the physician to be able to video conference in. So there was a big alarm button on the Android tablet. You can push on that and then you go. They called me because they had a scalability issue. They run to about 20,000 patients and they weren't able to scale from there. Now that's easy enough to do. This is 1 million patient, 10 messages per second, 10 million messages per second. I can build a cloud solution that handles that, no problem. I could put up a Kafka broker here or a cluster. I could write a processing cluster in let's say, Apache Spark or Flink or so on. This will be simple. But the goal is to produce various projections. This is for the nurse, had a patient dashboard. Physician would get calls whenever the nurse thinks you need to talk to the doctor. There were, of course, accountants looking at this and all kinds of other views. But this is, it's not, I mean, it's not trivial, but it's is something that I can solve. But when you look at this, well, I didn't discover it at first. It took me a few days of working on this before I realized that why are we doing this? Because it's going to be quite costly. For example, if you move all of these events to the cloud and process them there, 1 million patient, 10 messages per second on average from each patient, that's 10 million per second. That's 864 billion per day, assuming that's a 2 kilobyte average message size. That's 1.6 petabytes per day. So your mobile operator, if you're using that, is definitely going to send you a Christmas gift. In fact, they probably send their private plane down to pick you up for the Christmas party to give you that gift, because you're going to be spending a lot of money with them. So the insight I had here is, why are we not utilizing the Android tablet that is already sitting there? At that case, it was a dual core tablet, but now you can get these Android tablets that have TensorFlow or TPUs in them, that are quad core CPUs and lots of memory. But this is a decade ago almost. So maybe it is a decade ago. I'll have to go back in the calendar and check. But this Android tablet wasn't really doing anything. It was sitting there waiting for a video conference that might be happening once every week on average. And it collected Bluetooth event and passed them on. So it's mostly idle. So if we utilize that tablet, can we improve on this? So then it became a question, can I send the algorithm that I would run in the cloud down to the edge? Yeah, there could be security around this, and we had to really worry about it. But let's take a look at, can I send the algorithm down? Can I execute the algorithm? So the good news here is that every patient is its own island, right? There is no reason for me to look at another patient to figure out what to do with this patient. So I can easily look at only the events that are coming from a single site, and then I could process it there. Now, instead of sending these petabytes up now, the 1.6 petabyte per day was reduced to 63 gigabytes, which is 5 orders of magnitude better, right? And it dramatically decreased the cost of the cloud service too, because I didn't have to process it in the cloud. It was already processed before it got to the cloud. 3 orders of magnitude actually better, or less money spent on the cloud cost. I used an adaptive algorithm that reacted locally, and it also gave me the advantage that, most of the times the patient had other people living in there, so I could now react to alarming or a bad situation where a patient needed attention, even if I was disconnected from the network. Remember the intermittent network connectivity. Even if I was disconnected from the network, I could now react by sounding an alarm and getting people around to deal with it. So jitter and latency definitely reduced, right? And another interesting thing is its scalability, right? Because I was putting these Android tablets out anyway. Now, every time I got a new installation, I got a new computational unit. So I was paying for the, I was gaining capacity as I was installing different devices. So huge, huge difference. Right. Okay. Another thing that mistake, and my mistake was I didn't really see it at first, but I did see it after a few days. I could introduce it. But I think I've learned a lot from that. And every time I now do something, I look, where could I best process something? Another thing a mistake that I've made, and I see other customers do it too, is that I'm not mapping out the network topology, right? So when we build our software, we don't really care. So I'm going to connect to Mongo, yeah, wherever. We'll figure it out later. But you have to know, how are our edge computers connected? How do we get to them? What are the routers in between? What are the bridges? What are the quality of service on each one of these network segments? What is the jitter? What is the latency? What is, all of these different properties? And how will my software handle those changes, right? So I'll give you an example of a failure that we had actually at Pratexo. And the context here, we talked to a customer that wanted us to put out a set of edge computer on some edge sites that they had. And they explained to us that all the edge sites were connected with optic fiber. So we went, oh, that's great. Optic fiber, high bandwidth, virtually no jitter, no latency. We can put together a Kubernetes cluster using micro K8s or K3s or K0s for that matter. And we can deploy tools such as Kafka to manage the edge traffic. Great. This is brilliant. What we didn't ask is what kind of topology do you have? So when we went out to the field and we installed this, it turns out that all of their devices were daisy chained. So there was a central site, but then the fiber was basically daisy chained between the different edge sites. So what happens now if you lose a connection is that you lose all of the devices. If you lose it in somewhere in the middle, you lose 50% of the devices. And is there one thing that Kafka doesn't like? It is losing a lot of nodes at the same time. So it was a disaster, right? Now, in our case, we could fix it by simply looping things back again, and we convinced the customer to configure a ring, which made it a lot more stable and we could use it. And we actually went away from Kafka also, just in case, the daisy chain was done physically sometimes where it went in to the edge side and out basically in the same conduit. So you could easily so imagine this happening at the central side, so you can easily break both of them. So we ended up ditching Kafka for something else, but it's an example where we did not ask the right question. So nowadays, whenever we build a solution for a client, we try to map out the whole network that we're going to install things on to identify these kind of issues. So lesson learned, some software, fiber in the data center isn't the same as fiber at the edge, right? You need to know more. Some software is designed to run in very stable environments, for example, Kafka, as we used in this case. And now we always map the network topology. Some of the best practices, I think, are embrace a user-centric design approach. So understand your requirement and the constraint of the edge network. Implement robust error handling or recovery. So assume networks at the edge will fail. But what is your strategy when you fail? You can't just tell me, oh yeah, then I'm done, or you crashed and burned. You have to have an acceptable way of recovering from that. You have to have an acceptable way of handling the offline case. Now, it could be that you can't do anything because the network is down. That's fine, but don't crash and burn. Right? Process the data at the first possible opportunity. Now, I know people are going to protest on this because they want all the data up in the cloud because that's where you're going to do the training for machine learning. And that's fine. Then send it up. But very often you could do massive improvement by just processing things in real time, collect the data, compress the data, and then send it up for machine learning later. For example, let's say we're building something for a ship, right? And we have all kinds of equipment on the ship that we're collecting data from the machines, from fuel consumption, or navigational paths, whatever we're collecting data for. You can make all the decisions of what to do, right? Reduce the RPM to save fuel, or the scheduling and everything. You can do all of that locally. You may still want to collect all the data, but wait until you get to shore. When you're docking, the communication cost is significantly less than when you're on the sea. And if you're using that data for learning, why send it up in real time, right? You can do a learning with some weeks of delay for sure, right? So that's another thing, right? Incorporate security at every possible stage. And the decision may be, I don't need security here. And that's perfectly fine, right? But you have to ask the question. And the testing has to be realistic. You need to be able to inject network failures into your testing. And there are all kinds of tools for that. If you do a little search on the internet for that, you'll find a set of tools. We tried them all, and it makes a huge difference. There are some future trends here that I think we will see. Things like 5G becoming more and more prevalent, which means that clustering techniques such as Kubernetes becomes more and more practical. We see a lot of artificial intelligence, machine learning at the edge. I don't know if you can, there probably is a video of me here, but like one of the things we used is, I don't know if you can see this camera, maybe if I put it in front of my face, but this is a camera from Axis that has a Google TensorFlow chip in it. You'll see edge devices, sensors that are specifically for that. This is a device sensor that we created to be able to listen to the frequency of the net, so we can react to or do what's called FFR, fast frequency response. But it reacts in milliseconds to a grid degradation, so that we can help by turning things off and so on. You'll see more advanced edge analytics, edge as a service, where you basically are paying for someone to do the edge computing for you, and you don't worry about buying the hardware and so on. We've been spending a lot of time on being sustainable, often by moving processing to the edge. We can dramatically improve the carbon emission, for example. Integration of IoT and wearable, more and more of these sensors. We've seen some need for blockchain at the edge in some cases. We have autonomous system, particularly autonomous cars and so on, coming online. And there's still a bit of a lack of standardization. So I think we see a lot of changes to that too. But if I am to take some questions, I should probably stop here, which is fine because this was the last slide. So let's take question, Aiden. Do you have any questions for me?
Yeah, great stuff, Petter. Thanks so much. We do a couple questions, and there is still time if you want to throw one in the chat. Definitely feel free. But yeah, let's start it off here. So our first question, does 5G solve most of the issues that you've discussed today?
No, it does not. So 5G still has some issues. Well, first of all, 5G doesn't really help with the jitter. It does improve latency by far, but if you have an edge site that, for example, where the computer is sitting in a metal cage and you get the Faraday effect, it doesn't really help, right? If you have a moving device, it might be moving from 5G to 4G. So it does allow me to, in places where the network is more stable, to apply a set of solutions that I would use in a data center. So it does help, and it does allow us to push more data up, but it's still expensive. I mean, we've had, as I showed you, there was a 3-order magnitude better cost, or 5 orders of magnitude better cost on how you deal with, or in the mobile network. It's still expensive to send data on mobile network. If you're a big enough company, you could probably negotiate really good deals, but it's still expensive. Also, I'll discuss that in a later talk where I'm going to look at the economy of edge computing. The different vendors have different ways of charging you. So, for example, here in the US, Verizon charges you per byte sent. AT&T and T-Mobile charges you per frame sent. So if you send 1 byte, you're paying for 1K, or at least it used to be that way. So depending on, so you have to understand how they charge you also. But yeah, I don't think 5G is going to solve this. It's going to allow me to do other use cases like streaming videos and things like that easier. But it's probably not going to solve these things. You still have to assume network goes down and so on.
Great. Another question we have. So how can you take a great engineer and turn them into, or kind of mold them into a great architect? What's kind of your tips for that?
Right, that's a good question. Okay, so a great engineer moving, so an engineer is their modus operandi is divide and conquer, right? You get a big problem and you split it into smaller sub problems and smaller again until you can solve it, and then you solve them sort of one after another. But you assume a certain set of given. I'm going to build it in this language. I'm going to build it on this database. I'm going to do this set of things. An architect must have a holistic approach, and they want to delay their decision of how they do it to the last possible moment. And not and I don't mean that they should get into analysis and paralysis, but they want to keep their option open because you're looking at every aspect, right? You're trying to evaluate it in as many aspects as possible. The best engineer is someone that has good knowledge in as many of these aspects as possible, so they can look at something from a security perspective, from a recruiting perspective, from a, whatever perspective, scalability, availability, whatever. And they have the right questions to ask. They don't necessarily need to be the expert on everything, but they need to know how to conduct a question. And it's also often a matter of how do you present it. So I've seen great architects that can work on their own, but you have to sell it to everyone else too. So there's another challenge. But yeah, as I said, I've been teaching classes on that for a long time. And I would take a look at things like IEEE 1471, like Sackman framework is a good way to looking at things, trying to get a holistic view and make the decision when you're comfortable that you've gone through enough of these aspects so you can score them, and then be able to justify it.
Awesome. I think we have time for one more question here. Before we get to it, I do want to remind people, as it shows on the screen, if maybe you don't want to ask your question live or anything like that, you can always reach out to Petter directly at his email or his LinkedIn. He's a very friendly guy, as you can tell from our webinar today. And yeah, definitely reach out to us with any questions or projects or anything that you have. So let's get into the last question here from Arun. I hope I pronounced that right. So specific to networks, do you see new age players like Megaport playing a role in edge computing? If so, what can be their value to customers?
Yeah, so I have to admit that I haven't looked at Megaport, so I probably should be very, very careful of doing that. I know that they do this cloud interactivity and simplifies that, but I haven't studied them in details. I don't know if the cloud vendors or the cloud connectivity is going to simplify the world too much, right? Because the key thing is to get connection to the edge and getting reliable connection to the edge. So we're doing a set of things for that. Like you see a LoRaWAN spreading out. I don't know how that's going to handle things, but where you can sort of expect to have the ability to talk to your LoRa devices. Advantage of LoRa is obviously a long range connection. You see 5G being built out. But even in countries like, take Norway as a good example, because they have spent a ton of money on infrastructure, and any Norwegian expect to be able to use their cell phone anywhere. Or if they're in a tunnel, if they're on subway or whatever, they expect that their cell phone will work. And if it doesn't, they complain, and someone will put another more infrastructure because they can use their oil money to do some of these things. So even when I sat on a mountaintop in Norway and far away from anywhere, I still had connectivity, right? I could still talk. Even in those areas, when I was running an experiment, I was losing connectivity at selective places. So I think it's many of these network challenges that I see aren't really in cloud interconnectivity, but it's really on the connection from the edge to wherever you need to be, to your data center, to your cloud. I think you'll see the mobile operators starting to put cloud services out locally on their 5G stations and so on. But it's your connectivity to wherever you need to get to, right? That is the challenge today. Getting a reliable connection is really what's the biggest challenge. But I should take a look at Megaport and see if I could see something in them that, and if I do, maybe I'll write a blog article or so on that. But I don't really know Megaport that well, so I know of them, but I don't really, I haven't really used them. So.
Awesome, sweet. Well, thank you so much to everybody for joining us, and thank you to Petter for a great presentation. As I said at the beginning, we will be sending out a recording of this webinar as well as a link to the white paper that Petter mentioned, which goes more in depth to everything he discussed today. So check your emails that you registered with for that. And yeah, thank you so much. Any final closing words from you, Petter?
No, I'll just thank everyone that came to the webinar, and hopefully it was useful. And don't be afraid of reaching out.
Awesome. Thank you all.